Everyone, welcome back to Hackaday Remoticon. Our next speaker, Debra Ansell, has spent the last decade making things blink. You might remember her exquisite leather and LED handbag from a few years ago. Nowadays, she is creating modular PCBs that form dynamically reconfigurable electronic systems for PCB-based displays and wearables. In other words, she's still making things blink, but in cooler ways. Earlier this year, we covered Debra's interlocking triangle light panel sculpture that uses a clever electromechanical interconnection system in the form of spring contacts. Today, she will speak all about the building blocks of modular PCB design. Please welcome Debra Ansell.
Thank you. I hope everything sounds okay. Hi, I'm Debra Ansell, and thank you for attending my talk on modular systems of printed circuit boards, generally known as PCBs. As was said, I've been building electronics, mostly LEDs projects for over a decade, but I only learned to design PCBs a few years ago. Perhaps because it's a recent skill that I'm still building, I often find myself exploring non-standard ways to apply it. And a brief digression that's not in my notes, I have been tremendously enjoying the wonderful talks at Remoticon thus far, and was a bit anxious that I think my talk has a little bit lower information density than the previous ones, but I hope that after absorbing so much information, if you're watching this live, that you'll enjoy listening a bit more to the process and looking at some bright blinky LEDs a little bit. So let's go to share screen if I can get this going. Okay, this should be okay. Let me know if it's not, but I think I'm now sharing screen. All right, so in a project, PCBs are usually used for their electrical function, but they can make good mechanical building blocks as well. When circuit boards are a construction material, their shape and the ways in which they connect determine the form and function of the final project. This talk will show several different kinds of modular circuit board designs created by me as well as other makers. I frequently post new builds online under the screen name Geek Mom Projects, and my motto is LEDs improve everything. My projects obviously reflect that philosophy. As these pictures show, a lot of my LED projects are wearables. I first learned to design PCBs because I wanted to create my own LED wearables product line called Bright Wearables. And in that process, I designed and manufactured an LED accessory board for the microcontroller, which attaches with snaps to the interior of specially designed bags and backpacks. That's the idea that got me started with PCBs, but I keep finding new ways to use them in my projects. So the next few slides show modular PCB assemblies from a few other makers. There are no established rules or best practice techniques for creating modular PCB assemblies. The concept can be applied in a number of ways. The two projects shown here are kits consisting of PCB panels where the PCBs in the panel have different shapes and functions. The cat lamp kit at left, the PCBs in the panel are organically shaped with plated slots that solder together directly. Some of the PCB elements form the lamp's electronic circuit, but others only provide structure or decoration. The Hack Mod Wear Kit was created by Mary Etta West and Angela Sheehan, who both have wonderful, amazing individual maker projects online. They designed this kit for SuperCon 2018, and the PCB elements are designed to be separated and assembled into wearables. The elements have different shapes and components like LEDs, sensors, and processors, and you can create arrangements with different looks and functions by using different subsets of this kit. On this next slide, the projects are a different kind of modular PCB build. They are designed and assembled from many identical PCB base elements. These designs work by assembling simple PCBs into larger, interesting geometric shapes that come together and feel much greater than the sum of their PCB building blocks. On the left, Daniel Hinch's icosahedron build uses two different shapes of PCBs. The red pentagons have a neopixel in their center and are the vertices of an icosahedron, while the longer boards form the edges. The addressable LED signal travels along the soldered edges through a carefully mapped path that reaches each LED exactly once. The lamp on the right by Twitter maker Eric Bozeman, who goes as Brain Smoke online, connects irregularly shaped PCBs into a near sphere that has circular holes, which are pretty impressive because they're made from cutouts in the side. The design is amazing. So, and seeing how cool these aluminum PCBs look in this build has convinced me that I'm going to have to try out aluminum PCBs sometime. But note that in both these builds, the final form is fixed. It's predetermined by the shapes of the individual boards, which are directly soldered together. So my inspiration to make a modular circuit board system came from seeing nanoleaf light tiles. These are, like I said, light tiles which attach to a wall in different configurations and display colorful changing light patterns. Many manufacturers have copied this product, and many makers have been inspired to create their own versions. If you Google DIY nanoleaf tiles, you'll find many different creative ways to build similar displays. So I'm innately drawn to changeable art, especially if it has LEDs, but I found it hard to justify buying myself a set of tiles because I already have so many LED strips and strings at home. I set about trying to make my own version instead. It turns out that most of my modular builds, which you'll see in this, some of which you'll see in this presentation, have a lot of common elements with the nanoleaf tiles, which makes sense because they're intended as art. And the traits here are qualities I usually try to incorporate in my modular designs. So first off, I usually use identical base circuit boards in my project because it's simpler to design and usually more flexible to rearrange the elements. The circuits themselves are simple, again, because it's easier. Complexity comes from the way in which the circuit boards are assembled or programmed. The PCBs are self-connecting because I prefer to minimize the number of different parts in a build, and the builds just tend to look cleaner that way. I like easily reconfigurable projects because your tastes change, and I think it's fun to be able to rearrange your art to match. They're scalable because I want to be able to use the same base elements for a small project or a big project. I like that flexibility. And of course, LEDs. My goal is always blinky bright, colorful, and attractive builds because that's my aesthetic. Now, of course, making custom PCB projects requires that you design your own PCBs, which I initially found intimidating. Now that I have more experience, I thought I'd share my secrets to low stress PCB projects. And I swear this slide is not just an excuse to work a Dr. Strangelove joke into my talk, but that was a bonus. I really hope to encourage more novice makers to learn circuit board design because it's such a powerful tool and to have in your maker toolbox. This one single element can provide your build with electronics, aesthetics, and mechanical support. So it's easy to make mistakes when designing and ordering circuit boards. And I used to worry about wasting time and money. Circuit board design software has a steep learning curve, and the process of ordering boards is confusing. So here's my secret to overcoming the fear of making mistakes with PCBs. First, start by reading tutorials on how to design them. I found the Spark Fun tutorials on using EagleCAD very helpful when I got started. Second, review your designs carefully, have a friend check them, send them off, place an order. Don't sweat the details because it's the third step here that's critical. Inevitably, you'll make mistakes, but you'll also find those mistakes are rarely a big deal. You can order small prototype PCB runs cheaply. If you find some mistakes, use it as a learning opportunity, revise the design, and redo the order. It's not that expensive to experiment. I felt better about making so many mistakes when an experienced circuit board maker told me that sometimes even his orders came back only functional as coasters. So most PCBs you see in builds have been redesigned and tested through several iterations. They're rarely perfect the first time. So ultimately, the trick to low stress PCB projects is simply not to stress and just try out your ideas to see what happens. I have learned more from my mistakes than my successes and have a bonus collection of really weird shaped coasters now. So this slide shows how some of my previous projects contributed to the design of the PCB-based light tiles. I had built a series of what I called inner glow projects that embed an LED strip sideways into laser cut acrylic sheet. The LEDs shine directly into the plane of the acrylic. The 3 projects on the left use that technique. These projects, which place the LEDs inside the acrylic, gave me the idea of how to design the light tiles. The base layer of a tile is a PCB with side-emitting LEDs covered with a layer of laser-cut translucent acrylic. The LEDs shine directly into the acrylic, which diffuses their light. Now, the pictures on the right show views of the final tile assemblies, which I made using both triangular and hexagonal tiles. You can see how the inner glow effect worked out. Each tile polygon has 1 LED at each corner, pointed towards the tile's center. The hexagon LEDs diffused more uniformly than the triangles, probably because they contain twice as many LEDs. And the non-uniformity of the triangle tiles is actually more pronounced on camera than it is in real life. And even so, it creates a pretty effect. And it is also actually dependent on the brightness at which you run the LEDs. So it still looks nice, even if it's not perfect diffusion. The circuitry in the light tiles is extremely simple. This schematic shows all the components in a triangle tile: 3 addressable LEDs, 3 decoupling capacitors, and 3 connectors. I included this slide to show you that you don't need to be an electronics whiz to make interesting PCBs. Super simple circuits can produce great results. So I made a few different prototypes of the tile PCBs, so their appearance may differ in some pictures, but this version here in the upper left have a solder mask story. These light tiles work best with a white surface on the top to reflect any downward directed light back into the acrylic. When I ordered them, white solder mask was more expensive than black, but happily it turns out that white silkscreen is free. So these tiles actually have black solder mask with a top surface almost completely covered in white silkscreen. I did my own assembly using the fancy skillet you see in the bottom row. Surface mount soldering with an inexpensive electric skillet is a neat trick I learned from another SparkFun tutorial. It's a great way for makers who are new to the process to assemble their own surface mount PCBs. I've since upgraded to a reflow hot plate, but absolutely recommend the skillet method if you're just getting started. I called out this SK6812 4020 side illuminating LED because I have a love-hate relationship with them. Side illumination is a really, really great way to let you view the LED's colors without it getting overwhelmed by the blinding glare. But these LEDs have teeny tiny pads and are a big challenge to solder. So consider yourself warned if you decide to use them. Once I had working PCBs, I laser cut translucent acrylic for the top layer with cutouts at the position of the LEDs and capacitors so it could sit flush against the top layer of the circuit board. And nylon screws hold the layers together and blend in nicely visually with the white acrylic. And this is how I made the individual light tiles. It was a bigger challenge to connect them together, but before I get into that, I'm going to digress for just a moment. So since I'm advocating using PCBs as a construction material, I feel like I should be able to tell you whether it's cost effective. So I did some simple math. PCBs and acrylic are the 2 main components of the light tiles and cover the same surface area. So it's reasonable to compare their cost per tile. The calculations here use retail prices for the acrylic I used and PCBs minus shipping and tax. So at left, we see that cutting 33 acrylic tiles efficiently laid out on a 12 by 24 inch sheet of translucent acrylic cost about 54 cents per tile for materials only. And on the right, it turns out that ordering 50 lead-free circuit boards with black solder mask from JLC PCB averaged 84 cents a tile, which is a little over 50% more per tile for the PCBs than the acrylic. But the PCB cost will drop at higher quantities. And if I didn't own a laser cutter, I'd have to pay to have the acrylic laser cut, while the PCBs arrive fully cut and drilled with whatever customizable silkscreen artwork I want at no extra cost. So I think that if we're going to examine the cost effectiveness hypothesis of PCBs as a construction material, I would call it confirmed. So now back to the tile construction. As I said before, connecting the tiles was the hardest part, though that's not unique to this project. I find that in most of my builds, the biggest challenge is figuring out how to connect and hold everything together. I wanted the light tile assemblies to be reconfigurable so they couldn't be soldered together directly. I needed to find a connector. And the first step was to figure out what I needed. I identified these characteristics: mechanical strength, because unlike the real nanoleaf tiles, which used a wall for support, I wanted my build to be freestanding. Electrically, the LED data signals needed to travel through a long chain of connections in a potentially very large assembly. And for safety reasons, I didn't want exposed power contacts. Aesthetics were really important because this is functional art. I wanted unobtrusive, low-profile connectors, and they also had to be surface mount because any through-hole parts would stop the acrylic sitting flush against the circuit board. Affordability is important because of the sheer quantities of connectors required. Each edge of each tile has a connector, and there are many tiles in a large assembly. And part availability is a bigger issue now than it was at the time, but even then, I didn't want parts that would be obscure or hard to get. So with these criteria established, I started to search and became intimately familiar with the board-to-board connector categories on Mouser and DigiKey. There were a lot of potential candidates to sift through, and you'll have to humor me for another brief digression, because when I was writing up this portion of the talk, it struck me that the connector search was actually starting to sound a lot like dating. So briefly, these are the similarities I noticed. With so many possible candidates, it really feels like it should be easier to find the right one. Second, when you're searching online, an effective filter is very helpful. And the biggest similarity to dating is that you start out with like certain ideals in your mind and take a good hard look at what's available and realize pretty soon that there are gonna be some compromises. So back to the connectors. I did consider a lot of candidates and none were perfect. You could potentially apply dating metaphors to this slide as well. The connectors shown here were actually among the sturdiest I could find, but none of them could support a vertical column of PCB light tiles by themselves, and most of them were expensive. The one actually that came closest to meeting all my criteria was surprisingly also the simplest and cheapest. Surface mount header pins were easily available, flexible enough to survive a bit of stress, but still not strong enough on their own. So in the end, I created my own connector by designing a second circuit board, you see here. The fiberglass cores of PCBs make them good structural reinforcements. On these connector PCBs, power and signal pass through small pressure connectors that have little spring-loaded prongs that can move up or down. I chose pressure connectors over header pins because they require fewer parts, since header pins work in header socket pairs, while the complement to a pressure connector can be a simple solder pad, which is basically free. So the pressure connectors were also lower profile and had a smaller footprint. To keep them from getting squished, there's a laser cut 1/16 inch layer of clear acrylic with cutouts on the connector side of the PCB. And in the assembly, what I really liked is that these custom connectors completely covered the contacts, so electronics were not exposed. And this video shows the tile assemblies running some simple animations. I want to point out that the stands for these structures are just wooden versions of the PCB light tiles that I laser cut with slots so they could be cross-braced perpendicularly. So these cross-braced bottom layer of wooden tiles are just attached to the bottom row of light tiles in the same method as the light tiles attached to each other. And they make a really nice, adaptable, actually pretty good looking base. So it worked really nicely, but it wasn't perfect. And as usual, the connections were the issue. The larger assemblies had some mechanical issues, mostly because of torque from the combined weight of the tiles. There was some sagging in the plane of the tiles, and also what was worse was that the bending perpendicular to the plane of the tiles could sometimes be enough to lift the pressure connectors completely off the contacts. So I think that tighter tolerances and smaller gaps between tiles would help future builds. To shore up the existing build, I laser cut some small clear acrylic shims to just slide between the tiles, and added extra laser cut acrylic connectors for extra support. Tightening the screws helped with electrical connections. And in future designs, I think it would be a good idea to place the electrical contact points as near to the screws in the connectors as possible, and maybe even add some more screws to really hold things together tightly. Electrically, this is probably a novice mistake, but I really hadn't thought enough about power distribution. If you route power in a single line, the voltage drops significantly by the end of the tile sequence, making LEDs dimmer. So I added extra power taps to my assemblies, but in future revisions, it's best addressed by redesigning the connectors. And without too much detail, the PCB connectors I made only attached the input of one tile to the output of another, so they only work along the signal path. It would be better if they could distribute power between any adjacent tile edges, which would be most easily accomplished by making all the pinouts on the edges symmetric at the connection points, like this example down here in yellow. And that would also help with safety, because it's harder, probably not impossible, but harder to hook symmetric connections up wrong. But despite, or probably because of the challenges of this build, I've really enjoyed having these displays in my house. So that was the first, but not the last, of my modular PCB builds. And just to show that they can't all be winners, this was my attempt at a wearable version of light tiles. I scaled the project way down, way down. And at this side, the only detachable connectors which fit were these 1.27 millimeter pitch through hole header pins, which turned out to be really difficult to solder. I was able to construct a working assembly, but it was ugly. And in the end, I just scavenged the tiles to use in a wired cuff bracelet project instead. So I still had PCB light tiles left over and wanted to use them in a 3-dimensional build. So I joined 8 of the tiles into an octahedron. I 3D printed some screw brackets to hold the sides together at the right angles. The wiring, a Gemma M0 controller, and a LiPo battery all fit inside the octahedron, and I didn't need to make the wiring neat because it's not visible from the exterior. Adjacent tiles in each build half were soldered together, so they couldn't be reconfigured, but the screw brackets did make them quite sturdy. The 2 octahedron halves snap together with neodymium magnets, and the final build has a nice futuristic look when illuminated, and I would really like to create more 3D PCB light projects in the future. Now, this next project has a bit of a twist, pun intended. I couldn't stay away from the idea of creating modular PCB wearables, so I thought I'd scale up a little and make a cuff bracelet, a flexible cuff bracelet. Wearable builds are a special challenge because they need to conform to our irregular bendy bodies, and I wanted a bendy connector. So I'm not really sure where I got the idea to use dollhouse hinges, because I certainly did not find them on Mouser or DigiKey, but they're appealing because they're cheap, small, and have screw holes for reinforcement. They're brass, which can be soldered. So I designed a footprint for them, then fabricated small PCBs to use as links in a cuff bracelet. Adjacent links connect with 3 hinges for power, signal, and ground. Each link has 3 layers. The PCBs sit between a laser cut acrylic bezel on top and the hinges on the bottom layer. Wires go through the matching holes in all 3 layers for mechanical reinforcement. So in this build, the side emitting LEDs fit inside cutouts in the bezel, which I filled with hot glue for light diffusion. I covered the exposed back of the hinges with black tape to insulate it and make it more comfortable to wear. And as you can see here, the aesthetics were terrific. I love the way this looks. The hinges are very low profile, making the bracelet quite thin. The assembly flexes smoothly and easily. Unfortunately, there were electrical issues. You don't see it in this video, but repeatedly bending the hinges causes glitches in the LED patterns. And after playing around a bit, I believe that it's the friction between the hinges and the pins holding them together, plus having large open metal surfaces for signal creates interference on the signal line. I did not continue with this project because I couldn't figure out a good way to overcome safety issues of having a wearable running current through large regions of exposed metal. Also, under stress, it turns out that the pins inside the hinges can slip out and cause shorts, which is obviously bad and even more obviously bad inside a wearable. So while they were fun to play with, I've stopped using them and strongly recommend that you don't use dollhouse hinges in your electrical projects, just in case you were tempted. But I still did want to find a way to make a bendable PCB assembly and tried a different approach. A Twitter recommendation pointed me to these rotating connectors. They only cost about 60 cents a piece, have 4 circuits, and even better, they're actually designed for use with PCBs. So these connectors give a much safer and more reliable electrical connection. Unfortunately, I didn't find them that attractive in a wearable, and they aren't very strong mechanically. They separate too easily under stress. So a running theme in this talk is that it's very difficult to use the same PCB connector for both electrical connections and mechanical support. So next up, more motion. This is my articulated PCB projects, also known as Bendy Boards. It's another moving PCB assembly, but it uses a different technique. With the hinged builds, the boards move perpendicular to one another, but this design rotates the boards within the same plane. The full assembly is a chain of pivoting links. Each removable link consists of 2 parallel PCBs with holes in the center that pivot around a common axis provided by a plastic push rivet. The links use the same pressure connectors as the light tiles did, except in this case, the pressure connectors make contact with a ring-shaped pad on the surface of a rotating PCB. Each ring in the pad, each ring on the PCB makes contacts with 2 pressure connectors on the other board in the link, and this redundancy helps maintain the connection in case there's a bit of wobble. Just like with the light tiles, there is a buffer layer of acrylic to keep the pressure connectors from getting crushed. The other connector in this design is a small mezzanine connector, which joins links together detachably. 2 M2 screws on either side provide additional mechanical reinforcement to keep the links together. It was a fiddly, iterative design process to get all the tolerances right, but the result is actually remarkably sturdy and doesn't glitch even with a lot of handling. I'm really fond of this project, though I haven't found a good purpose for it other than a fidget toy, but I'm still thinking about ways I could use this design as a practical technique for flexing other circuit board designs. So fortunately, I have a little time left because we're at the last project of my talk. And this one is fun because I'm still right in the middle of it. I have not yet explored its full potential. I haven't even shown it publicly before because I couldn't. I only just recently finished assembling a few of the PCBs, and here they are. The left side shows the unpopulated boards, and the ones on the right show that when populated, they contain 2 addressable LEDs, decoupling capacitors, header pins, male and female, and very short header pins, male and female, and a double pole, double throw slide switch, and the function will become clearer shortly. This was the first prototype of this design, and there was a significant mistake, but after a lot of unnecessary, I won't explain it, but basically in the end, the silk screen is on the wrong side, so which is fine as long as you're really, really careful about knowing which is voltage and ground. So by themselves, these boards aren't very exciting, but when you put them together, things start to get fun. These LED boards are another light tile project, but instead of the PCB forming the face of the tile, these little circuit boards form the sides instead. So this is how it works. The castellated edges of these PCBs can be soldered together at any angle, which means you can make a light tile in any shape with as many sides as you want, as long as all sides have the same length. So the same base PCBs can create a variety of shaped tiles. To hold the configuration in place, the tile faces are just laser cut translucent acrylic with slots to hold the tabs at the sides of the PCBs. The acrylic diffuses the LED light and also doubles as a jig for soldering the castellated edges, which is a nice efficiency. Using translucent acrylic on both sides of the tile gives you a two-sided display, or placing mirrored acrylic on one side just gives you a brighter glow on the other. I left holes in the acrylic to use standoffs to help hold each tile together, and the slide switches on each side determine whether that side is an input or output, and it's designed to work no matter how many sides are in the shape. So in any tile, one side gets set as input and the rest is outputs. And I'm running short on time. I'm going to count on the fact that I have, I think, a minute or two of overage because I'm close. So I've only had time to make a few working triangle and square tiles, but I have plans for different shapes, and there are a lot of possibilities. As long as you place slots in the acrylic, which correspond to the PCB tabs, it's pretty easy to assemble. So, all right, I know I'm getting closer. So once you've built the blocks, all you have to do is slide the header bins together, and voila, you have a rearrangeable modular assembly of modular PCB assemblies. And I have some additional ideas to try with these blocks because the holes in the PCBs, you see right here, allow adjacent tiles to be reinforced with standoffs, or you could put magnets in there and use pogo pins to make snappable magnetic light tiles, which I think would be fun. So all of this is going to be future experimentation because magnets like LEDs make everything better. And just to wrap it up, because I know I'm really getting close to going over, I hope that you see that there's a lot to be done with modular tile assemblies and that PCBs make a terrific construction material for projects. They also make good DIY connectors when you can't find an existing connector you like. Remember never to use dollhouse hinges as connectors, and I hope that somebody watching this talk will be inspired to go out and try using PCBs in a way they haven't thought of before. Thank you very much.